Welcome to the second lecture of this week. So remember, we have seen the so-called Cayley-Hamilton theorem. I made an introduction in the last lecture, and in this lecture we are going to write the actual theorem without any proof. So remember, I was working on the matrix, so 2, 2, 1, 1, and I have said to you that the characteristic polynomial of this matrix was s squared minus 4s plus 3. Okay? And the characteristic equation corresponding to this matrix would be the following: d of s equals to 0. Okay? So this is the characteristic equation. And Cayley-Hamilton theorem is related to whether the matrix itself, A, satisfies this characteristic equation. Okay? So here we are wondering about d of A is equal to 0 n by n. And this is the characteristic equation for the matrix. And Cayley-Hamilton theorem basically says that yes, the matrix A satisfies its characteristic equation in this form. Okay? So we are wondering about here a squared minus 4a plus 3 identity is equal to 0, 2 by 2. Okay? And this equation is always satisfied by any matrix. So if you have any square matrix, and if you write this characteristic equation, if you substitute A instead of S, then you will see that the equation is actually satisfied with the right hand side equal to 0 n by n. Okay? So now we're ready to actually write the Cayley-Hamilton theorem itself. So this is Cayley-Hamilton theorem. So every n by n matrix satisfies its characteristic equation. What does it mean? It means that d of A is equal to 0 n by n, where, of course, d of s is the characteristic polynomial, determinant si minus a. Okay? And instead of s here, and d of s is in general has the following form: s to the n plus d1 s to the n minus 1, d2 s to the n minus 2, going until dn. And d of a equals to 0 n by n means a to the n plus, I'm substituting s equals to a here, d1 a to the n minus 1 plus d2 a to the n minus 2 going until dn. Here I cannot put here a scalar. I need to put here the identity transformation, which is the identity matrix. That is equal to 0 n by n. Okay? So that is my characteristic equation. Here I have only scalars, and here the matrix version, which is the Cayley-Hamilton theorem. So now we would like to explain this theorem a little bit. We are not going to see the proof in the lecture. It's available really in the literature in lots of places. So we are not going to prove this, but we're going to look at its meaning. And we are going to look at this in the form of a remark. This remark tells us that Cayley-Hamilton theorem basically says that and higher powers, order powers of an n by n matrix can be written as a linear combination of its lower powers, lower order powers. Okay? So what does that mean? So let us look at this equation. So I have a to the n plus d1a to the n minus 1. This is going like this, and I have 0 n by n on the right. So here I would like to leave this a to the n on the left and take all the other terms to the right. Okay? So it tells us that a to the n is equal to, I have minus d1 a to the n minus 1 minus d2 a to the n minus 2. These minuses continue until minus dn identity. Okay? And identity is nothing but the zeroth power of a matrix. Okay? So we see that in this equation, a to the n, the nth power of the matrix A, can be written as a linear combination of its powers between 0 and n minus 1. So in this equation, nth power can be written, or is written, let us say, is written as a linear combination of powers between 0 and n minus 1. Okay? So Cayley-Hamilton theorem's intuitive meaning is just this one. So when you take the powers of a matrix, so when you take the zeroth power, first order power, second power, and n minus second power, when you reach the size of the matrix, a to the n, when the power of the matrix reaches n, the new matrix that you obtain, a to the n, is no longer linearly independent with the earlier powers. Okay? Because I can write the nth power of the matrix as a linear combination of its powers between 0 and n minus 1. So nth order power of the matrix is no longer linearly independent with the powers of the same matrix between 0 and n minus 1. Okay? So this is really a very, very interesting fact. When you take the powers of a matrix, you cannot always obtain linearly independent matrices. So the linear independence stops at the size of the matrix. And we are going to see actually the linear independence can sometimes stop even earlier at the smaller powers than n. And that is going to be related to the minimal polynomial of a matrix. So we have seen the characteristic polynomial. We are going to see another polynomial of the matrix, which is called the minimal polynomial of the matrix. And that is going to tell us what is the smallest power where this linear independence actually ends. That is going to be told by the minimal polynomial of the matrix. But Cayley-Hamilton theorem tells us that this linear independence for sure stops at the size of the matrix. Okay? And here the remarks tells us something stronger actually. It basically says that nth and higher order powers of an n by n matrix can be written as a linear combination of its lower powers. So it doesn't only says that nth order, it says that if I take n plus first order power of the matrix, then that is going to be also linearly dependent with the earlier powers. If I take the 2nth power of the matrix, that is still going to be linearly dependent with the earlier powers. Okay? So how can I understand this? So I will come back to here. So I have showed you that this is really satisfied. So by using this equation, I can actually write the following. In this earlier example, n is equal to 2. So A has size 2 by 2. Okay? So here the characteristic polynomial has the power order 2 here. So that means that the second power of the matrix, A squared, can be written as a linear combination of the earlier powers, 4A minus 3 identity. Okay? This is told me by the Cayley-Hamilton theorem, because this equation holds. So I can write the second power of the matrix as a linear combination of its zeroth power and its first power, okay, which is the matrix itself. And now I'm wondering about A cube. Can I write A cube as a linear combination of A to the 0 and A to the 1? The task here is really simple. So I can write this A cube as A times A squared. And I know that a square is 4a minus 3 identity. A, 4a minus 3 identity. And if I do this multiplication, I would get 4a square minus 3a. Okay? And I have again an a square here, which I can replace with 4a minus 3 identity. 4 times 4a minus 3 identity minus 3a. Okay? So then I would have here 16a minus 3a is 13a, and I have minus 12 identity. So you see that I can write a cube as well in terms of a to the 0 and a to the 1. Okay? So here, this fact that I can write the nth order power of the matrix as a linear combination of powers between 0 to n minus 1, actually, I can actually generalize it to higher powers. I can write any nth or higher order power of the matrix as a linear combination of its 0 to n minus first power. Okay? So this remark just claimed that one, and if I would like to do that for a to the 4, a to the 5, I can do it here. I can write any power of this A matrix as a linear combination of identity and A for a 2 by 2 matrix. So now I'm wondering about whether I can generalize this thing a little bit more. What about A inverse? A inverse is the minus first power of the matrix. Okay? Do you think, and this remark doesn't tell us anything about it. It only tells us positive powers and higher powers. Okay? And what about A inverse? So the interesting thing, so I'm wondering about if I can write this as alpha times A plus beta times identity. Okay? And the answer is going to be interestingly yes. So here let us remember the characteristic equation for that 2 by 2 matrix. So I had a square minus 4a plus 3 identity is equal to 0 2 by 2. Okay? Let me multiply both sides by a to the inverse. So a to the inverse, I have a square minus 4a plus 3 identity is equal to still 0 2 by 2. And a squared times a inverse is a, minus 4 times a inverse times a is identity, plus 3 times a inverse identity is a inverse. Okay? And that is equal to 0 2 by 2. All right? And now I can extract A inverse from this equation. 3A inverse is equal to minus A plus 4 identity. And I would divide both sides by 3, which is going to give me minus 1 over 3A plus 4 over 3 identity. So you see that I could write A inverse as a linear combination of A to the 0 and A to the 1 as well. Okay? So I could really do it. So that I could write the negative power of the matrix as a linear combination of its powers between 0 and n minus 1. Okay? So actually this remark can be generalized to the negative powers of the matrix. And actually any power of a matrix can be written as a linear combination of its powers between 0 and n minus 1. Okay? So this is really a very, very interesting and magical fact about matrices. So here, at the very end of this course, we're going to define actually the exponential of a matrix, e to the a. Okay? So in this case, we're going to use the following thing. So I have the e to the s as a power series, I from 0 to infinity, s to the I over I factorial. Okay? And then e to the a is going to be defined by the following expression. Instead of s, I will write here a. I from 0 to infinity, a to the I factorial. Okay? So you see that if you would like to therefore calculate the exponential of a matrix, then you can use the power series representation of the exponential function, scalar exponential function. Then this is going to be another matrix which is given by this summation, where you sum the powers of the matrix by dividing them with I factorial. Okay? So you know that here, in this case, by the Cayley-Hamilton theorem, we can write any power here as a linear combination of powers between 0 and n minus 1. If this is e to the 2, 2, 1, 1 matrix, then I know that any power here can be written as a linear combination of, so I would have I from 0 to infinity, a to the I can be written as alpha I times a plus beta I times identity. Okay? So I can actually write this as alpha I a plus beta I identity over I factorial. So now I can take a parentheses, I from 0 to infinity, alpha I over I factorial, a, plus I from 0 to infinity, beta I over I factorial times identity. Okay? So you see that this is a scalar times a, plus this is a scalar times the identity matrix. So you see that I could write e to the 2, 2, 1, 1, where this is my A matrix as a linear combination of A and identity here. Okay? So here if I call this coefficient as alpha and call this coefficient as beta, then e to the A for this matrix is nothing but alpha A plus beta identity. Again, a linear combination of the powers of A between 0 and n minus 1, where n was equal to 2 in this case. So at the end of this course, we're going to see the concept of a function of a matrix, okay? Like exponential of a matrix, okay? Or sine of a matrix, or cosine of a matrix, or logarithm of a matrix. And in that case, we are going to use this expression. Any function of the matrix A can be written as a linear combination of the powers alpha 1, a to the n minus 1, alpha 2, a to the n minus 2, going until alpha n, and I have identity. Okay? If I have an n by n matrix, I would have this. If n is equal to 2, then any function of A can be written as alpha 1a plus alpha 2, this is n minus 2, okay? And alpha 2 identity, okay? I can actually write such equalities. Then finding a function of a matrix will turn out to be equivalent to finding these unknown coefficients. Okay, I will have at most n unknown coefficients, and finding them will find us the specific function of A that we are looking for. Okay? So really these parts are not important. We are going to see them in more detail in the last lectures of the course. So if you didn't understand what I did here, it is really not very important. We will repeat them. So here, before I continue with the topics, I would like to do something interesting. So here, let us go back to our example. I told you I like this matrix a lot. So I have here the eigenvalues were lambda 1 is equal to 2, lambda 1 is equal to 3, and lambda 2 is equal to 1, and the eigenvectors were 1, 1, and the eigenvector for the second one was 1, minus 1. Okay? So now I would like to do something interesting. I would like to calculate what a to the 100 is. Okay? A to the 100. At the end of this example, we are going to see that 100 is not really a specific number. I can here replace it with any number here, and then I will be able to find a solution. Okay? So this is, of course, a power of a matrix, and you can obtain this by multiplying A with itself over and over until you reach the power 100. Okay? But really, I do not want to do this, but I would like to use the Cayley-Hamilton theorem. Okay? So so this is the question. So if I would like to do it using the Cayley-Hamilton theorem, I can write the equation a to the 100 is, this is a 2 by 2 matrix. So Cayley-Hamilton theorem tells me that this power is going to be a linear combination of the power 0 and 1, because n is equal to 2. Okay? So I know that by the Cayley-Hamilton theorem, a to the 100 can be written as a linear combination of the identity matrix and A. Okay? So now I'm wondering what are alpha and beta. If I can calculate them, if I can calculate these numbers, and then I will know what a to the 100 is. Okay? So here is what I'm going to do. I will use this equation, and using this single equation, I will be able to calculate what alpha and beta are, and then I will be able to calculate a to the 100 by substituting those coefficients into this formula. Okay? Here is what I'm going to do. So I will multiply, so this is a matrix equation, so I can multiply both sides of this equation with the eigenvector. Okay? A to the 100, E1, is equal to alpha A E1 plus beta, identity times E1 is E1 itself. Okay? So this is going to be my first equation, and the second equation is going to be, I will multiply both sides of this equation with the second eigenvector. A to the 100 E2 is equal to alpha A E2 plus beta identity E2, which is E2 itself. Okay? Then these two equations are going to give me a means to calculate what alpha and beta are. All right? So for that, I need to know what is a to the 100 times E1. I know what a times E1 is. It is lambda 1 times E1. Okay? So a to the EI, if I have an eigenvector, then when I multiply it with the matrix A, I would get lambda I EI. Okay? Because eigenvector satisfies this equation. But what happens when I take the square? A square EI. What do you think this is? In this case, I can write this as A times AEI, okay? Because A squared is A times A, and AEI is lambda I EI, okay? Lambda I is just a scalar, it can get outside, so lambda I AEI, okay? So then here, I can actually, again, use the formula AEI lambda I EI here. And that is going to give me the following. Lambda I, instead of AEI, I would write lambda I times EI once more. And this is going to be lambda I square times EI. Okay? So we see here that A square EI is equal to lambda I square EI here. This is very nice. So when I multiply a power of a matrix with the eigenvector, then the result happens to be eigenvalue to the same power times the eigenvector. Okay? You can actually go with this logic, continue with this logic to write the following. A to the power, let me say, j times EI is equal to lambda I to the power j times EI. Okay? So this is a fact about matrices as well. So if you multiply the jth power of a matrix with the eigenvector, then that is going to be lambda I to the power j and times the same eigenvector. So this eigenvector equation is a specific case of this generalization for j equals to 1. Okay? So now I will use this fact here on these equations. All right? So a to the 100 E1, the first eigenvector, this is going to be lambda 1 to the 100. Lambda 1 is 3. So I have 3 to the 100 E1 is equal to alpha. AE1 is lambda 1 E1. So that is going to be 3 E1 plus beta E1 itself. Okay? And the second equation is a to the 100 E2 is lambda 2 to the 100. Lambda 2 is 1. So 1 to the 100 E2. And that is equal to alpha lambda. This is AE2. It's lambda 2 E2. I have 1 E2 plus beta E2. Okay? E1 and E2 are non-zero vectors. So now let me try to simplify these equations. So the first equation is 3 to the 100, and I can take E1 parenthesis here, 3 alpha plus beta E1. Okay? And 1 to the 100 is 1. So there is an E1 still here. 1 to the 100 is 1, and I have here E2. That is equal to alpha plus beta E2. Okay? Now E2 and E1 are non-zero vectors. That means that the coefficients of these vectors should be equal. Okay? In both equations. So I get 3 alpha plus beta is equal to 3 to the 100, and alpha plus beta is equal to 1. Okay? So now I have two equations, two unknowns, and I can solve these two equations to find alpha and beta. Okay? Now let me first subtract the second equation from the first. That is going to give me 2 alpha is equal to 3 to the 100 minus 1. So that is going to tell me that alpha is equal to 3 to the 100 minus 1 over 2. Okay? And beta is 1 minus alpha from the second equation. Beta is 1 minus alpha, and that is 1 minus 3 to the 100 minus 1 over 2. And this is going to be 3 minus 3 to the 100 over 2. Okay? So we have calculated alpha and beta, and now all I have to do is to substitute here into this formula. So I would have here a to the 100 is alpha, which is 3 to the 100 minus 1 over 2 times a, 2211, plus beta, which is, beta is 3 minus 3 to the 100 over 2 times the identity matrix. Okay? So you see that there is a really very simple formula of the power, the 100th power of the matrix, once you know actually the Cayley-Hamilton theorem. Okay? You don't really have to take the powers of the matrix by multiplying it with itself over and over. And actually here I can do the following. If I am wondering about any power of the matrix a to the j, here this 100 really is not a specific number here. I can actually write the following. Instead of 100, I can put here any power j over 2, and I have 2211 plus 3 minus 3 to the j over 2, and I have 1001. Okay? So I would have just this type of formula. Okay? So here, for example, I can use this formula to calculate what a to the 0 is. A to the 0 is, it should be identity matrix. So 3 to the 0 is 1, 1 minus 1 over 2. This is going to be multiplied by 0. 3 minus 3 to the 0, 1. So 2 over 2 is 1. So I would have this one as identity. Or I can look at a to the 1. And here I can write it as follows. It is going to be, of course, a itself, 2211. And in this case, when I substitute j is equal to 1, this coefficient becomes 0, and this becomes just 1. Okay? So you see that you can write an arbitrary power of a as a linear combination of some powers of a between 0 and n minus 1, where n is the size of the matrix. And all of this comes from a single theorem called Cayley-Hamilton theorem. Okay? So the Cayley-Hamilton theorem tells us that we can write any power of A, which is nth or higher order powers, in terms of the powers between 0 and n minus 1. And why is that? Why does it make a claim of nth order? Because the characteristic equation, the Cayley-Hamilton theorem equation, is just this one. Okay? And in this case, d of A, d of S was an nth order polynomial. Okay? That is why the Cayley-Hamilton theorem is making a claim about nth or higher order powers. If I can find another polynomial, okay, another polynomial instead of the characteristic polynomial, which would satisfy the same equation, I can actually make similar claims. Okay? For example, if I find another polynomial, m of A, which satisfies this equation, and if the order of this polynomial is smaller than the characteristic polynomial, then I would be able to make the similar claims for lower order powers of A, lower than nth order, if m has order less than d. So it is really important for us to know polynomials which would satisfy this type of equation. And actually we are going to be wondering about what would be a polynomial which would satisfy this equation, and what would be the smallest order polynomial which would satisfy this equation. Okay? So I want the order of this polynomial m as small as possible. And that actually brings us to the concept of so-called minimal polynomial. Okay? So we will be asking the following question. Suppose that we have of course, by Cayley-Hamilton theorem, this equation is always satisfied. But we are going to ask the question, do we have a smaller order polynomial than the characteristic polynomial which would satisfy the same type of equation? And the answer is sometimes yes. For some matrices, we can find actually polynomials which would have smaller degree or order than the characteristic polynomial, which would satisfy this type of equation. And those polynomials would become really very, very useful, because we know that, for example, for this matrix, actually the linearly dependent power starts from 2. Okay? If I have a lower order polynomial that would satisfy the same equation, I would actually know that the linearly dependent powers might start at earlier powers, at smaller powers. Okay? So therefore we are going to be asking that question. So can we find lower order polynomials than the characteristic polynomial which would satisfy similar equations to the characteristic equation? Okay? So I would like to illustrate this idea with an example. Okay? In the example, I have the following matrix. A equals to 2, 2, 1. So this is my matrix. And the first thing that I'm going to do is to calculate the characteristic polynomial, d of s. When you look at a matrix like this, a diagonal matrix, an upper triangular matrix, or a lower triangular matrix, you need to be able to tell me the eigenvalues immediately without making any calculations. When you have an upper triangular matrix, a lower triangular matrix, or a diagonal matrix, eigenvalues are always the diagonal elements. Try to show this, try to prove this yourself. Okay? So the eigenvalues of this matrix would be 2, 2, and 1. Okay? So the characteristic polynomial would be s minus 2 squared and s minus 1. Okay? So I know that this, by the Cayley-Hamilton theorem, when I substitute A into this polynomial, I would get just the 0 3 by 3 matrix. Okay? So I will just write it. So what is d of A? D of A is, I'm going to substitute here, instead of S, I will substitute A. So I have A minus 2. This is wrong because I cannot subtract the scalar 2 from a matrix, okay? So I need to put here 2 identity square, and I would have A minus, instead of 1, I will write minus 1 identity, okay? So this is D of A, and I know that this is definitely equal to 0 by the Cayley-Hamilton theorem, okay? Let us try to show it. A minus 2 identity is a matrix when I subtract from the diagonal elements A just 2, okay? Subtracting 2 identity from A means that I need to subtract 2 from the diagonal elements of A. So A minus 2 identity here, this is going to be 0, 0, and I would have minus 1, and zeros everywhere else. The square of this thing, and A minus identity. Subtract 1 from the diagonals. Then I would have 1, 1, 0 here, zeros everywhere else. So Cayley-Hamilton theorem tells us that this multiplication should be equal to 0, okay? So now I'm going to write this in the long way. So this is the square of this matrix. So I would have 0, 0, minus 1. And since this is the square of a matrix, I would have 0, 0, minus 1. This is a square. And I would have the matrix, the other matrix. So this is A minus identity. Okay? And this is 1, 1, 0 here. When you multiply diagonal matrices, all you have to do is to multiply their diagonal elements one by one, okay? So really you do not have to make a long matrix multiplication. Just multiply the diagonal elements of the matrices. So when I multiply these 3 diagonal matrices, I would end up with another diagonal matrix. The first diagonal element will be the multiplication of the first diagonal elements of these individual matrices. 0 times 1 is 0. 0 times 0 times 1, 0, and minus 1 times 0, 0. Okay? So this is nothing but 0, 3 by 3. Okay? So we see that we actually justify the Cayley-Hamilton theorem for this case by substituting into the characteristic polynomial our A matrix, and then we showed that the result is D of A is equal to 0. Now I will ask the following question. Can I find a lower order polynomial than the characteristic polynomial? Here, the characteristic polynomial is third order. It has 3 roots, okay? And characteristic polynomial of any matrix is nth order if the size of the matrix is n by n, okay? And in this case, I am asking the following question. Can I find a smaller order polynomial than D of S, which would satisfy a similar equation to the characteristic equation? D of A is equal to 0, 3 by 3. Here, this was nothing but D of A. Okay? D of A is equal to 0, 3 by 3. Can I find a lower order polynomial than the characteristic polynomial, which would satisfy the same equation? And for this matrix, the answer is actually yes. Okay? And here, you can actually see it here. Suppose that I remove one of the factors here. I had a square. Suppose that I remove this square from here. Okay? When I remove this square from here, it would be just the multiplication of these 2 matrices. And what would be the multiplication? 0 times 1, 0 times 1, minus 1 times 0. It would still be equal to 0. Okay? So we see that if I remove this power here, I would get the polynomial s minus 2, s minus 1. And that polynomial has a lower order than the characteristic polynomial, and it would satisfy a similar equation as the characteristic equation. So I will define here m of s is equal to s minus 2, s minus 1. And in this case, what is m of a? M of A is A minus 2 identity and A minus identity, and this would be A minus 2 identity is that matrix 0 0 minus 1, and I'm not writing the off diagonal elements here, they are all 0. A minus identity is 0 0, A minus identity is 1 1 1 1 0. Okay, and this multiplication would still give me a diagonal matrix with 0 elements on the main diagonal. Okay, but this is nothing but 0 3 by 3. Okay, so we see that we have found a lower order polynomial M of S. It's second order, and the characteristic polynomial was third order. And this lower order polynomial would still satisfy a similar equation to the characteristic equation. Okay? So I can still continue asking questions here. Can I find an even lower order polynomial which would satisfy this equation? And the answer is going to be no. Okay? For this example, there is no lower order polynomial than this M of A which would satisfy a similar equation. So in such a case, we would call this M of S the new polynomial that we have found. If we cannot find any smaller order polynomial that would satisfy the same equation, then we call this M of S to be the minimal polynomial of the matrix A. Okay? So M of S is the minimal polynomial of A. Okay? So in matrix theory, polynomial, because this course contains algebra in it, and the polynomials are very important ingredients of the field of mathematical field of algebra. Okay, so the matrix theory always connects with the polynomial theory in some places, and characteristic polynomial is only one of the polynomials which is important for the matrices. Minimal polynomial is probably the second one, and there might be lots of other polynomials that might be interesting or that might be important in the analysis of matrices. Okay, so this minimal polynomial is going to be our next topic. Let us write minimal polynomial. So we're going to first try to define what minimal polynomial is. The definition really is not going to be complicated, but it is going to use some concept like a monic polynomial. Of course, for example, the zero function is also a polynomial. Okay, which all of its coefficients are 0. So really, and it would satisfy such an equation trivially. Okay, so really we do not want to call it the minimal polynomial. Okay, so here, in order to exclude the zero polynomial, we are going to define the concept of a monic polynomial. Definition: a monic polynomial is a polynomial whose highest degree coefficient is unity, and which means that it is equal to 1. Okay? So we are defining the concept of a monic polynomial, and monic polynomial is a polynomial whose highest degree coefficient is equal to 1. So this is a trivial concept. So I can look at two polynomials here, s to the n plus alpha s to the n minus 1. So this is alpha 1, and I have alpha n. So this polynomial, this is a monic polynomial. Okay, because its highest order power, highest order term here has coefficient 1. Okay, or if I start instead 2s to the n, plus alpha 1 s to the n minus 1. Alphas really do not matter. If I start with 2 here, this is not monic anymore, because highest order coefficient is 2, and for a polynomial to be monic, it has to have the highest order coefficient equal to 1. Okay? Of course, characteristic polynomial is a monic polynomial. Okay? It always starts with s to the n, with the coefficient 1. Okay? So characteristic polynomial is always monic. D of s is equal to determinant si minus a is always monic. Okay? And we are going to require the minimal polynomial of a matrix to be monic as well. Okay? And here, as you see, the minimal polynomial of the matrix that we started with was this one, and this polynomial is monic. Okay? Why is that? Because the highest power of s here is s squared, and the coefficient of s squared is going to be 1. Okay? So this is a monic polynomial. So now we are ready to define the minimal polynomial definition. For an n by n matrix A, the minimal polynomial m of s is the monic polynomial with the smallest degree or order, with the smallest degree, such that m of a is equal to 0 n by n. Okay? Sometimes, for some matrices, we cannot really find a smaller degree polynomial than the characteristic polynomial, which would satisfy this equation. In those cases, minimal polynomial can be equal to the characteristic polynomial. But for some matrices, there are smaller degree polynomials than the characteristic polynomial, which will satisfy this equation. And in that case, the minimal polynomial would not be equal to the characteristic polynomial. Okay? In the earlier case, so when I look at this matrix 2, 2, 2, 2, 1, the characteristic polynomial d of s was s minus 2 square s minus 1, and the minimal polynomial was s minus 2 and s minus 1. Okay? And there might be other matrices in which the characteristic polynomial would be equal to the minimal polynomial. Okay? So don't think that minimal polynomial has always smaller degree than the characteristic polynomial. For some matrices, minimal polynomial is the same as the characteristic polynomial. There is no smaller degree polynomial which would satisfy this equation. I can just give you a matrix. So 2, 2, 1, 0, and I have 1. This matrix, the characteristic polynomial is s minus 2 square s minus 1. Okay? For this matrix, I have exactly the same characteristic polynomial as this diagonal matrix. This matrix is upper triangular, so its eigenvalues are the same as the eigenvalues of this diagonal matrix. So the characteristic polynomial of these two matrices are the same. But if you look at the minimal polynomials of these two matrices, you would see that the first one has a second order minimal polynomial, but the second one would have a third order minimal polynomial. Okay? So for the second one, the characteristic polynomial and the minimal polynomial for this matrix would be equal. Okay? But for the other one, they are not equal. But the eigenvalues of the matrices are the same. We are going to see why this is actually happening. Obviously, it's happening because of this 1 here, but we will investigate these cases in much more detail. So the minimal polynomial has some very, very important properties. They are really important, and we are going to try to prove them. Let us write these properties. So we have defined the minimal polynomial, and this theorem is going to give the properties of the minimal polynomial. Given A in C n by n, let m of s be its minimal polynomial. Then there are 3 properties. I will first write the properties, and then I will talk about what they mean. M of s is unique. This is the first property. So minimal polynomial is unique. There cannot be 2 minimal polynomials of a single matrix. There is only one and only one minimal polynomial for a matrix. Okay, there cannot be more than one. The second one is m of s divides d of s, the characteristic polynomial, without any remainder. Any remainder. Okay? The meaning of this is that there exists q of s, another polynomial, such that the characteristic polynomial is the multiplication of m of s and q of s. Okay? Q of s is just another polynomial. This was the second property, and the third property is going to be as follows. Every root of d of s, every root of d of s. These roots are eigenvalues, as we know. Eigenvalues. Roots of the characteristic polynomial are eigenvalues. Every root of d of s, which means eigenvalues, is also a root of m of s. Okay. So now let us talk about the meaning of these properties. All right? The first property is basic. It tells us that m of s is unique. Okay? So there cannot be more than one minimal polynomial for a single matrix. Every matrix has one and only one minimal polynomial. Let us come to the second one. The second property. It tells us that m of s divides d of s without any remainder. So here it would be interesting to give you some examples. Let us consider the earlier example. Suppose the characteristic polynomial of a matrix is just this one. Okay? In this case, the second property tells us that minimal polynomial for such a characteristic polynomial really cannot have the following form: s minus 2 and s minus 3. Okay? So the minimal polynomial for a matrix which has a characteristic polynomial, minimal polynomial really cannot be in this form. Why is that? Because in that case, m of s would not divide d of s without any remainder. Okay? So this s minus 3 really cannot divide this polynomial without any remainder. Because this is another root than the roots of this polynomial. So really I cannot have such a minimal polynomial because of this s minus 3. Alright? So here I really cannot have any other root than the roots of d of s in the minimal polynomial. So for example, m of s cannot be s minus 4 square either, Because s minus 4 square cannot divide d of s without any remainder. So in the minimal polynomial, there can only be the roots of the minimal polynomial can be only the roots of the characteristic polynomial. Okay, so here what can, and here this, for example, can the minimal polynomial be this one, s minus 2? In this case, this really doesn't violate the properties, because s minus 2 divides d of s without any remainder, right? Why is that? Because, sorry, this is m of s. Because if I divide this, if I divide d of s by m of s, in this case I would have s minus 2 square s minus 1 over s minus 2, and in that case I would have just s minus 2 and s minus 1. This division would happen without any remainder. So this m of s satisfies the second property. Okay, m of s divides d of s without any remainder. Or I can here put s minus 1 as well. This also satisfies the second property. This one also divides the d of s without any remainder. Or I can put here square. This polynomial also divides this d of s without any remainder. So what were the alternatives? Let me write them in a long way. I'm sorry, I'm erasing too much here. So s minus 2 doesn't violate the second property. S minus 2 square doesn't violate the second property. M of s minus 1 doesn't violate the second property. What about m of s is equal to s minus 2 cube? Can this be the minimal polynomial of a matrix having this characteristic polynomial? No, in this case, not, because this m of s cannot divide this d of s without any remainder because of this cube here. There is square here, there is cube, so there would be always a remainder. So this violates the second property. Okay, and m of s, can it be this one, s minus 2, s minus 1? Yes, this can be a minimal polynomial. It doesn't violate the second property. And what about m of s minus 2 square s minus 1? Yes, this doesn't violate the second property either. And what about s minus 1 square? M of s is equal to s minus 1 square. In this case, this violates the second property, because here I have the highest power of s minus 1 was 1, but this has power 2. So I cannot divide this d of s by this m of s without any remainder. So these violate the second property. Okay? So here, the ones that are not violating the second property are these three and these two. Okay? Is there any other? I'm not sure. So now let us look at the third property. Every root of d of s eigenvalues is also a root of m of s. So the third property tells us that every root of d of s, here the roots are 2 and 1, okay? 2 and 1 should be both a root of m of s, okay, according to the third property. All right? So what does this mean? When I come back to these possibilities which do not violate the second property, I see that some of them would violate the third property. Okay? So here I see that for this one, m of s has the root 2, but d of s has another root at 1, and this 1 is not a root of this m of s. Okay? So this violates the third property. Okay? I cannot have this as my minimal polynomial. It violates the third one. What about the second one? So I know that every root of d of s should be also a root of m of s. The roots of d of s were 2 and 1, and I see that 1 is not a root of this m of s. This cannot be my minimal polynomial. And this really cannot be my minimal polynomial either, because s equals to 2 is not a root of this one. So these three would violate the third property. Okay? So you see that when you start with a d of s, by using these three properties of the minimal polynomial, you can really eliminate lots of polynomials here. These cannot be minimal polynomials because they violate at least one of these properties. So you see that these two do not violate the third property either, because the roots of d of s are 1 and 2, and the roots of m of s are 1 and 2 again. So m of s, the second one does not violate it either. So you see that if you have this characteristic polynomial, by using these properties, you understand that there are only two possibilities for the minimal polynomial to be. Okay? It can be either this one and either this one. Okay? So, or this one. So you really cannot decide which one it is without looking at the matrix. Okay? I have seen here that for this matrix, the characteristic polynomial is that one, and the minimal polynomial turns out to be this one. But on the other hand, for this matrix, the characteristic polynomial is this one, and the minimal polynomial is that one. So without looking at the matrix, you cannot decide which one is the actual minimal polynomial. But you can really reduce the number of possibilities when you see such a characteristic polynomial. Okay? So then I can actually give you the following characterization. Suppose that our d of s is in the following form: s minus lambda 1 to the r1, s minus lambda 2 to the r2, going until s minus lambda k to the rk. Suppose that there are k distinct eigenvalues. Okay? And here, the characteristic polynomial should have the order n. That means that the sum of these powers here, the multiplicities in the characteristic polynomial, their sum should be n, r2, going until rk should be n. Because I want this in the overall to be an nth order monic polynomial. Okay? Now, what does the minimal polynomial look like? M of s can be, I know by the third property here, all roots of d of s has to be a root of m of s. Therefore, I need to replicate all of these eigenvalue terms here, s minus lambda 1, s minus lambda 2, going until s minus lambda k. Okay? But of course, in the minimal polynomial, I can have some multiplicities here. Let me call these multiplicities m1, m2, going until mk. Now, by using these properties that we have given, so we can actually give some ranges for mi's. Obviously, these are 0 or positive numbers. They cannot be negative numbers. Otherwise, if these are negative numbers, that would not be a polynomial anymore. Okay? So I have m1. Can m1 be equal to 0? It really cannot, right? Because if m1 is equal to 0, then lambda 1, which is a root of d of s, would not be a root of m of s anymore. Okay? Therefore, these mi's are always larger than 0. They are integers, and they are always larger than 0. They can be at least 1. They have to be at least 1. So maybe I can write greater than or equal to 1. Okay? And this is m1. Can these mi's be larger than the corresponding ri power? That cannot be, because if m2 is larger than r2, then it would violate the second property. You know, s minus 2 cubed cannot be really. It violates the second property because this polynomial cannot divide d of s without any remainder. Therefore, these mi's can be at most r equal to ri. Okay? So we have this type of property in the minimal polynomial. So minimal polynomial would always be looking like this, and these powers, the multiplicities in the minimal polynomial, would be always between 1 and Ri. Okay? And the summation of these Ri's are actually, it should be just n. Okay? So one final thing, I can tell you the following. Suppose that d of s is equal to s minus lambda 1, s minus lambda 2, going until s minus lambda n. And suppose that lambda I is not equal to lambda j when I is not equal to j. So we have the distinct eigenvalue case. In this case, what can be the minimal polynomial? According to these properties. So we see that each of the Ri's are equal to 1 here, because the eigenvalues are distinct, no repetition. Each of the Ri's are equal to 1 here for all I. So mi's are going to be between 1 and 1. So mi's can be only 1. Okay? They cannot be anything else. So that means that in this case, minimal polynomial would always be equal to the characteristic polynomial, s minus lambda 2, going until s minus lambda n, which is d of s. So in the distinct eigenvalue case, the minimal polynomial is always equal to the characteristic polynomial. Okay, that is an important fact coming from the properties of the minimal polynomial. So we are going to prove these properties of the minimal polynomial, because it is going to give us the interesting ideas about the minimal polynomial, and also there are going to be nice exercises in proving some properties. Okay, but that is going to be all for this lecture. Thank you very much for watching. Bye bye.